no such machine, no such Turing machine. Hence, there's no such algorithm. So nowadays, from now on, increasingly, well, we're equating an algorithm with a Turing algorithm. In other words, some Turing machine that executes that algorithm. And since all these computational models are equivalent to each other, it doesn't really matter which model you use. Like as I was saying before, Turing, Church, Clean, Post, whatever. All right, so let's concentrate now on this sort of simpler polynomial with just one variable, just x. Okay, and does it have? Can we create a Turing machine that would recognize it? Now, what does that mean? Well, if this, this is my, it's my interpretation, if this polynomial here does have an integral solution, then you can construct a Turing machine that will accept it, right? Now, that's it. So you can create machines that will accept strings or members of the set that satisfy the property. The property in this case is this polynomial with an integral root. That's the property. So you can find a machine that will accept such strings. Okay. Now, what if your polynomial has no root, no integral root? Well, then your Turing machine, there are two possibilities. It'll reject, or it'll loop. It may go on forever. Okay. So that's the problem. So if you cannot find a machine that will either accept or reject in all cases, for all strings, then you do not have a decider. Therefore, that language, all the strings in that language, that language is then undecidable because there is no Turing machine that can decide that language, meaning decides in the sense that either accepts or rejects. All right, so let's take this. So we're going to have a sort of simpler language now. We'll call it D1 rather than D. And the simplification is that the polynomial now is just over one variable. We'll call it x, just over one variable. Whereas before was an arbitrary number of variables. Okay, now here's now a description of a Turing machine, and the format that it's in we'll talk about more formally in later sessions. But it's in a format that Sipser will standardize for the rest of the text. And this is an example of that format. A particular way, in fact, the high-level description I was talking a bit about earlier, that we will use increasingly. Right. So we're talking about the design of a Turing machine, in fact, an algorithm, and we'll be de-emphasizing the Turing machine and just more emphasizing the algorithm, because the ChurchTuringThesis effectively says that algorithms are Turing algorithms. In other words, there's some algorithm, step-by-step process that a Turing machine can execute. Right? So when you hear the word algorithm, just think Turing algorithm. And after a while, the fact of how the algorithm is implemented, on what machine, given they're all equivalent, the machine implementation tends to drop away. You're de-emphasizing that, and you're concentrating more and more on the algorithm itself. All right. So here's a description of a Turing machine. Call it M1, and it's going to be a recognizer. It's a recognizing machine. In other words, if if the string that goes in, if it satisfies the property of belonging to the set, then that machine in one here will accept it. Okay. All right. Okay. So you'll typically, well, I'm getting ahead a bit, but I'll give you an example. Typically, you'll start off with a statement about that describes the input string, your W or whatever. Okay, so and usually, and the whole thing, like M equals, and you have an English type description, usually divided into stages which are numbered. In this case, it's only one stage, so just a single one here. And the whole thing in quotes, well, double quotes, right? Here and here, right? So starting off with a description of your input, the input string. So it's the input string just a polynomial over the variable x, and you may ask, well, that's a string. I mean, it's a polynomial. So the whole there's a whole discussion in later sessions on representation, like how do you represent, for example, a polynomial as a string? How do you translate this mathematical object polynomial into a string? So you need to do that. How do you translate a graph, for example, into a string? How do you represent, in other words, how do you represent a graph as a string? So all this translation, or what's called representation, it's a whole theory on representation theory. We'll talk about that in later sessions. So assuming you've taken your polynomial and you've represented it somehow, being a bit vague here, but you've translated that polynomial into the form of a string somehow. So you've encoded it, if you like, from polynomial into a string format. The Turing machine can then read the string and decode it, can do the reverse process and extract from that string the polynomial. Okay, so the Turing machine typically will have as input a string, and we'll talk about that in later sessions. Okay, all right. So the first thing is usually a description of the string, input string, and then one or more stages in English, so prose, English prose, giving a high-level description of the algorithm, what it's actually doing, right? So here, for this case, now we're trying to find a recognizer, in other words, a Turing machine that will accept those strings that represent polynomials that do have at least one, and integral root, right? The solutions. In this case, there's only one variable, x. So if x does have an integral value that makes all this 0, then that value of x, that's a root, right? A root's just a solution to the polynomial. For the variables. There's only one variable, so we're trying to find trying to find the value of x. Okay, so here's the algorithm. So evaluate p. In other words, find out what the value of this is for given values of x, and so you just systematically go through all the whole range of integers, right? So 0, plus minus 1, plus minus 2, plus minus 3, and so on. So you just successively go through all integers and use the Turing machine to test whether plugging in each integer value into this polynomial, do you get 0? Okay, and the moment you do get 0, the Turing machine will go into an accept state and stop. Okay. So it has recognized a string that represents a polynomial that does have an integral root. Okay. Now, so if the polynomial evaluates to 0, then your Turing machine will accept. Okay. Now, so if P polynomial does have an integral root, then your machine will, if you can see that, will eventually find it and accept. Okay. Now if your polynomial does not have an integral root, then this machine M1, now you probably can't see the second line, but I'll just read it out a bit, getting into the next session. Then your machine M1 will run forever. Okay? And that by definition is looping. That's looping. And a machine that loops does not decide. Okay? So that Turing machine, and hence that algorithm, is not deciding. Now, if there is an integral solution, an integral root, then the machine recognizes, but it doesn't decide because it may be going on forever. Okay, I hope now you're clear on that distinction between deciding and recognizing. Okay, so till next session.